So, hello again. Now I'm going to present about profiling memory in Lua, and a little bit about me. You all guys know I kind of like a little bit of big data. I'm doing research at PUC in Brazil, and I pretty much started playing around with Lua in 2008, so it's been quite a while. And about this talk, it pretty much started in my master's, and it was kind of in 2011, and there was like a big wave until right now, when it was kind of almost published. Some problems here, big gap in the middle, then I came back, more problems, and finally the work was out there. It started a little bit with garbage collection, so let's study a little bit of Lua's garbage collection, what's going on. Then it went a little bit about memory leak and what is memory leak, it's a bad definition and things like that. A lot of study over Java, and let's not go that path. And finally, how can we help users identify and debug memory issues? So that was kind of the main concern of the work at the end of everything. So how can we help people that kind of are having problems with memory? How can we help them to identify and, of course, try to fix these kind of problems? So the agenda for this talk is pretty much the problem itself, so what we consider as a problem, what were the existing tools for Lua at the time, the proposed tools, so the tools that I've created, and pretty much how was the evaluation of the tools, how they perform, what they are useful, whether they are useful or not. So it's all about memory consumption. Okay, so you have a program, it's running, now we have tablets, iPhones, Androids, and these things are with a very low amount of memory, and memory came back to being a resource, all right? So how can we kind of tackle that and help people use not a lot of memory? So first thing is pretty much memory bloat. So we have a lot of terms out there, and it was kind of a big confusion, like whether it's a memory leak, but memory leak is about C memory leak, and how do we address memory leak when it's kind of garbage collected language, and then became like a lot of terms, and all right, let's get a big term, pretty much memory bloat, and let's think about it with memory consumption that exceeds the program expectations. So sometimes you're just writing a compiler and it's using a lot of memory, but you just don't care when you are kind of compiling, because it takes like 10 seconds, 15 seconds, and it's probably not gonna run out of memory, and it's not your problem. When the compiler ends compiling things, all the memory is gonna be given back, and that's not an issue. So you only have a problem when you actually have a problem. So let's try not to create problems. So the main cases about memory bloat is pretty much object churn. So when you keep creating new objects and garbage collection is being triggered again and again and again, so you are wasting resources, both CPU and RAM. Data structure misuse, so depending on the language, you can decide to use a data structure, but that's not the optimal data structure for your use case. And sometimes you can lose a little bit of memory on that. Memory leak. So this is memory leak in C. As we know, you pretty much forget to free some kind of object, and you don't have the pointer anymore to do it later. And another case, pretty much memory hoarding, which is what people call memory leak in Java or memory leak in garbage collected languages. And it's pretty much like not removing useless reference. So the object is valid, but it's not used by your program from now on. So it's just like a useless object, all right? And what are kind of the main problems that we have here? So first of all, program execution slowdown. So if you're using more resources, triggering garbage collection, you're pretty much, your program is not running as fast as it could. Second of all, in some cases, you can get system slowdown. So the entire system gets to kind of stop performing as it should because of one execution. And finally, you can get like program crash. So everything, your program stops working and responding just because of that. So the existing tools at the time was pretty much Lua Memory Profiler, which actually was not an option. It was based on Lua 5.0, and pretty much the basic features it added were kind of implemented in Lua 5.1. So it was kind of useless, needed to recompile the interpreter, it was not a good fit. There is Profi, which dates from 2012, and it had pretty much an execution time focus. So it was profiling pretty much execution time and not memory. It had like one memory function that you need to kind of manually call every time you want it. So you need to put like start profiling, stop profiling, and then you get back the results of pretty much how was the use of this chunk of code. Lua Traverse was released pretty much in 2006, with the last update in 2010, with pretty much some kind of small changes, not really much improvements. And the idea of Lua Traverse is pretty much traversing reference to live objects and applying a given function, so you could kind of count references and or find all paths to an object and things like that. So it was kind of useful, it is, but it was kind of limited in some ways. And there's also Microscope, which was released in 2013, and the last update was 8 months ago, so it's kind of seems like an active project. And pretty much what it does is you call a function, you pass a Lua object, and it dumps the Lua values of this object into a file using the GraphVS format. So it's a table. It's pretty much going to write an entire table, and then you can generate a graphical visualization of the graph if it's a complex object. So what were we proposing, what we tried to do? So pretty much there were like two projects. The first one was Lua Mem Profiler, and the second one was LMProf. Not very good with names. Sorry for that. But anyway, and the guidelines for developing these two tools were pretty much like, first of all, they should be easy to integrate into existing programs. So if you're writing an application, you don't want to waste a lot of time profiling memory. You just want to get your solution and see if things are working the way they should or not. So it should be really easy to integrate. Second of all, not too much overhead, and too much is, of course, depends on your use case, depends on what you want. So what is too much? Depends a lot, but we try to kind of minimize the overhead of the library when you were using it. And of course, it should provide readable reports, and especially for regular programmers. So you don't need to be a memory specialist or even a Lua specialist to pretty much understand what's going on and that things are working as they should. So the first tool I'm going to talk about is pretty much Lua Mem Profiler. And the motivation for that was kind of real-time visualization. So I wanted to give the programmer the flow of the memory allocation. So I wanted to show to the programmer how the memory was being allocated along the program execution. The second thing was kind of explore the type, class, data categorization, which is very used in a lot of projects of memory profiling. So it's pretty much like getting type information or class information and giving feedback to the user about memory regarding these types or categories. And finally, ongoing interaction. So I wanted to give the user the opportunity to kind of profile memory and stop at some point and investigate some object or some things, look into something more, and then continue the execution, and then kind of stop again and things like that. So this is what I built. It's not a very good interface. I'm not so fond on UIs, but anyway. And the idea here is that this is kind of your memory, and it starts on 0 over here, and it comes over there, kind of increasing from left to right. Each small block over here is kind of an object, and we kind of use the relative address, so things are the way they kind of are in memory. You can kind of use different commands to kind of filter. So if you just want to look into strings, you can press S and kind of just untoggle string or toggle string. You can clear everything, and you can use the N button to kind of do next. So it's pretty much kind of execute the program until the next allocation and then stop. And here you can kind of see a small stack trace, okay, with kind of 3 lines, something like that. You can use your mouse to kind of zoom in and zoom out. I just do 1 level zoom for now, and that's pretty much it. So at the end of the execution, what you get back, it's like a final report. It's kind of summary of the execution itself. So you can see the number of mallocs, the number of reallocs and frees that were executed, but not only the number of operations, but also the size related to the operation. One important thing is that the realloc size is pretty much the sum of both positive and negative ones. Okay? So it can be kind of tricky to understand the realloc size. Also, you get back the number of mallocs of each type. So this is kind of the type data categorization, and you can see the number of strings, functions, table, others, and things like that. And at the end, this is kind of the maximum memory usage. It's pretty much the maximum distance between your first object allocated in memory and the last object allocated in memory, which is pretty much the size that you kind of need to be able to represent inside the interface. So the implementation. The implementation was not very, very complicated. Everything was built pretty much using the Lua set log have. And it's pretty much like changing the allocation function. So every time that Lua allocates an object internally, I get this allocation function. I get the value of the object that I am allocating, and they pretty much go on. So I can get all the information. I use simple counters to pretty much kind of keep the numbers regarding the allocation. And I pretty much use a hash table that I built in C and auxiliary lists to kind of keep everything together so I can draw it again. So if you just want to draw strings, I can just go over the string list and redraw it and things like that. So what are the problems associated with the implementation of the Lua profiler? The first one I had was the finalizer. So when you change the allocation function, you need to kind of unchange it when you stop using the allocation function. Otherwise, it's going to be collected at the end of the program, and the next object to be collected will call your allocation function, and there's no allocation function anymore, so it just blows everything away. So you need to set up a finalizer kind of restoring the original allocation function. And the second problem was the categorization. So the idea of separating objects by data types to get a lot of information was not like very useful. There are some internal problems, limitations that we found that we cannot get a lot of information. For example, regarding tables, all we have is pretty much like the pointer to the table, but not the internal information of the table itself. So it's kind of not very precise. And of course, the display was kind of a problem how to build it. So I'm not a very fan of UIs, I'm not very good in it. And I tried to kind of define a static size and kind of draw everything in size to not need to dynamic redraw the interface every time that you are allocating an object outside the screen. And it turns out that's not like a very good solution. Maybe redrawing it every time would be better, or using a different library. I used SDL, and I didn't have, for example, like scroll bars, so maybe using a scroll bar so you can scroll and keep looking to the memory, it's a good solution. I don't know. So LMProf was the second library, and the motivation around it was pretty much gproc. Okay, it's a very known tool and very common model using it in a very many different profilers. So it's pretty much kind of a function profiler. So what you get back in terms of information about your program, it's pretty much on a function level. So how much each function has usage of memory. And it's kind of an after execution report. So you first of all, you run your program, and when your program finished, now you can pretty much analyze the generated information and get the report and the information about the memory usage. So we have two kind of reports. The first one is the flat report, and it shows you the number of functions they are really showing and the total number of different functions your program has. You have the percent of memory that each function is using. So here I have the NV function, which stands for the new VAC function at line 29, and it's using like 392 megabytes. We have shallow and retained memory, and shallow memory is pretty much the memory allocated by the function itself, without children or anything like that. While the retained memory is the function allocated by the function also as a parent. So if children allocate different amount of objects, it's also accounted in the retained one. The number of calls, this is pretty much from gprof2, so the memory by call, I don't think this is very useful at all. So considering to pretty much remove it. This is the second report that we got, and it's pretty much a call graph. So the first one's kind of a summary of everything, while this one's a more detailed information about it. So what you get is pretty much the dashed line is the line that's accounted for. So here I'm talking about F1, and F1 has 160 megabytes of retained memory. So as a parent, a lot of function beneath it allocated 160 megabytes of memory. However, F1 is not allocating any memory at all. It was called only one time, and it called like two different functions, F2 and F3. F2 was called 2 times, and these 2 times that F2 was called, 2 of them were called by F1, and F3 was called only 1 time. So this is the retained memory they allocated, and the shallow memory they allocated. And now you can pretty much follow the call graph allocation. So if you come to F2, you see that F2 was called by F1. And if you take a look into F4, you see that F4 was called like 12 times, and 5 of them were by F2. And in these 5 calls, it pretty much allocated 50 megabytes. So if you jump into F4, you see exactly a little bit of this with a little bit of this. And also, if there is a recursive call, you get it in parentheses. So F4 is calling itself like 5 times. So how was the implementation of LLM-prof? So we also use the setAllot function, which pretty much changes the allot function, the allocation function that we're using, so we can get some information. And we also use the Lua set hook. So we're pretty much hooking function calls and function returns. So we get control, and we can do kind of the monitoring of the memory. I have implemented kind of a smart stack, which is pretty much an easier way to kind of deal with some kind of tail calls and cycles. And I also have a hash table with a caller-colleague pair where I store the information of every call. So the problems associated with it, again, the finalizer, it's exactly the same problem as before. As we are changing the allocation function, we need to remember to kind of restore it. All against memory allot functions. So one important thing about the reports of the LLM-prof library is that pretty much we only get information about the functions that are allocating memory. So we don't have information about the all function calls of the program, just the function calls that have allocated memory. So maybe it's interesting to kind of have all of them, as I am kind of hooking them anyway. So it was kind of a discussion about if it's going to be good or bad to have this kind of information, or even more important, if it's going to be useful or not. At the end, I decided to leave just the memory allocation function because it's more related to memory itself. Tail calls. So when you are doing the hook, you have special flags for doing tail calls, and these need to be treated separately because they work in a different way as a common function call. So I had to handle this. And cycles are actually a problem. So when you have cycles inside your function calls, you can kind of count the information regarding one function twice or more than 2 times. And you need to be able to handle that. And what most libraries do pretty much is gprof. It's kind of finding the cycle and transforming the cycle into one bigger object and calculating the memory for this guy. And that was not my approach. Actually, I decided a different one. So I kind of used the smart stack to get the information. So if you have cycles in terms of recursive calls, I can give you precise information. But regarding cyclic functions calling itself, I'm not handling that. So this is kind of a limitation. So how was the evaluation done? First thing that I was evaluating was pretty much the ease of use. So how easy it is to kind of use the library and pretty much how much do you have to change your program, your project to use it. The second thing was the report usefulness, which is pretty much how useful is the report in terms of finding memory problems and really understanding the report. And finally, the performance analysis. So what's the overhead that it impacts? So regarding ease of use, both tools are they use the same technique and they are very simple. So you just need to do a require and do a start in the library, and at the end you just need to do a stop. So it's a very easy change. You can do it manually, or you can even embed it in kind of a script to do it for you. And everything is exactly the same over here. All right? And for Lua Memory Profiler, you can pass an optional parameter to enable the display. So you need to pass here the size of the display in terms of memory. Regarding the report usefulness, I wanted to kind of really try the library and to kind of extract information regarding memory on an application that I had, for example, just superficial knowledge. So I got different applications that I pretty much have never used it and started playing around with the libraries to kind of get memory insights. So I used 2 programs. One is the Black and Scholes, and pretty much a financial application to classify portfolio options. And the second one is the Capture JPEG, which is an application to filter capture images for OCR. So these are the 2 applications that I got that I knew pretty much nothing, and I started playing around to get memory information. So regarding the Black and Scholes, the previous knowledge was pretty much the input. So it's a 1 million line file with 9 numeric columns. So probably there is a parsing on the lines and some calculation. And a lot of different values being calculated. That's pretty much all I knew. No line of code, no anything, and I started playing with the library. So the first one was Lua Memory Profiler info. And you can see the number of mallocs and the total size. So it's pretty much 1 gigabyte. And the maximum memory used is 700 megabytes, which means that at the same time, the memory you have 700 megabytes of objects kind of allocated. You can see the free. So the number of free is actually kind of big. It's pretty much, there's only 2 millions. However, the size of the free, it's kind of half here. Okay? And one thing that I do is pretty much to call the garbage collection before I end the library. So this free size is pretty much actually what was really free or what was able to be free. So you got also the types over here, so string, function, table, and others. And if you look at the display, you can see that kind of the allocation is pretty much divided in 3 phases. So you got a start, which is pretty much a lot of allocation, and then you pretty much kind of stops a lot of computation, then a small allocation, and finally another small allocation. So it's pretty clear that you got like this 3 phases. So the LM flat report pretty much tells you like the main chunk. It's pretty much allocating almost 1 gigabyte here, and it's responsible for most of the memory allocated. And you have kind of 3 main functions here. Insert a 4, which is 1 million, which makes sense because that's the number of lines. And you got a GMAT here that it's also 1 million, which is pretty much matching things. If you look at the code graph report, that shows you a lot of stuff. First thing, you see that it's very big. So you got like pretty much 700 lines with pretty much like a 4 iterator, which means like a new 4. And you can see the retained. In this case, it's not very clear or very insightful compared to the flat report. So after that, I pretty much knew I had to, if I wanted to get memory or to kind of decrease the memory usage, I should go into the main chunk and take a look into that, because that's where 1 gigabyte of it's being used. So it doesn't make too much sense to kind of waste time on the other part of the code. And yeah, so going to the code, I start looking into that, and you have like a data DB over here, and you got like some different a table with the different columns of the file. You got pretty much a 4 that's iterating over all the lines, and it creates a new table over here, okay? And it gets the fnum, which is pretty much 1, and it's incremented, and from here it consults like which column it is, creates this new guy in this table over here, and insert the option TB into the data TB table. So if you just keep looking a little bit, so here it's pretty much like creating a one big table over here with a lot of information and new small tables from here. If you go back down the code, you see that it creates a lot of different tables. So one for type, one for price, strike, rate, volatility, old time, which is kind of similar to what we have over here. And if you look, there is another 4 with kind of take a look into the option type and kind of iterates over the options and get the information from the data TB, I, the S, then it gets the strike, then it gets the R and the V and everything. So it's kind of writing data into one table. Then it's pretty much getting all this data from this big table and pretty much writing into other tables. Okay? So there's a lot of useless memory being used over here. Even this table over here, it's kind of being created on every loop. So I did small modifications, and pretty much what I did was bring this part down here a little bit up inside the main loop of the lines, and instead of leaving this table creation inside the 4, I kind of put it outside the 4 and reuse the table on every iteration, because the values are pretty much being overwritten, so you don't need to create a new table. You can use the same one. And the result was really good. Actually, we got like 7 times memory reduction using the Lua memory profiler results, and 4 times memory reduction using the user beam time application measuring memory from outside. And if you take a look here, you see that it was using like 1 gigabyte and that reduced to kind of 167 megabytes. Also, the number of mallocs pretty much reduced a lot, which can impact also the time that the script takes to run. In that case, was not impacting a lot because the amount of time, the major amount of time that was running was pretty much related to computation, okay, and not to allocation itself. Now you can see that number of mallocs is pretty much equal to the number of frees, which makes much more sense. So I'm pretty much freeing everything. And the memory usage also decreased. And of course, the number of objects is pretty much completely different. So string and functions, they will be the same because of the iteration of the file. However, the table here, the number of tables that we're creating, and also the other, which is pretty much the internal values, is much smaller. So the next application was the captcha, and there were like the input was 5,000 images, small images, 13 kilobytes, and a total of 65 megabytes. And all I knew about the application was this flow. So you have like an original image. It applies some grayscale, some other function, some other function, some other function, and finally it inverts and you get back this kind of image object. All right? And I started analyzing, so here again, the malloc size, the total free size, so it's pretty much okay, not much realloc. The maximum memory usage, it's pretty much like very small, so it's only 1 megabyte compared to 700, which means that objects are being kind of allocated and deallocated all the time. And if you take a look into the display, you see exactly that. Like you have a lot of objects being created and a lot of objects being collected again and again and again and again, all the time. If you take a look into the flat report, you see that you have like a JPEG string, which is pretty much using 80% of the memory. So if you want to reduce memory here, you should take a look into that function, or why is that function being called. You also have the read, which is pretty much reading the images, I imagine, which is kind of okay. And if we have like 65 megabytes, we are actually reading kind of twice the images. It's not a problem. 5,000 calls makes a little bit of sense. So we can check that, but probably there will be no issues here. If you take a look into the call graph profile, you can see very clear that the JPEG string is pretty much being called by threshold, grayscale, blur, and invert, which is pretty much the functions that I'm applying to each image, which are pretty much being called kind of 5,000 times sometimes. So threshold is being applied twice, which is pretty much clear here. And these are the guys that are using most memory in my program. So that's what I should go look into. So when I went to the code and started looking into the code, the first thing that I saw was pretty much the functions that were expected to be applied, and they were kind of being applied to the image and writing the image again. So it was kind of strange. So I was creating an image and writing the image again and again and again. And when I started digging into, for example, the grayscale function, there is kind of a create from JPEG string, and you get the image, and then what you do is pretty much get the image and transform it into string again, so you can kind of change things. So why not do that in place? Why do I need to kind of keep changing formats every time? So I enter a function, I change the format, and at the end of the function, I change the format again, but now I enter another function, and I do the same thing, changing the format and unchanging. So it was pretty much doing a lot of job, like absolutely useless. And what I did was pretty much change to kind of implementation of in-place change. So I pretty much just removed the create from and the transformation back here. I got back exactly the same results. And regarding memory, it was kind of 5 times less memory. So you can see on the malloc. And the memory used at the maximum is small, so it's pretty much creating small objects still. But you can also see a reduction in the number of strings and user data. So finally, the performance analysis is pretty much the overhead that it applies. So I use it more than just the 2 applications. So I have the black and shows, the JPEG, I have the captcha, but instead of using the JPEG format, I'm using the PPM format. There is a series which is pretty much a mathematical computation, There is a matrix multiplication. It's also a lot of calculations. And this is kind of a real application called Pablo. It's kind of a library, and that was used at Pookie in one of the systems that we have over there. And what you can see is that pretty much the white ones, the pure Lua, then we got the LM-Prof, finally the Lua memory profiler, and at the end you got the Lua memory profiler with the display. So if you compare just these two guys over here, so display without display, the display is not a big problem right now in terms of performance, except for some cases like the Placo one. Also in terms of time, you can see a little bit of increase regarding the LM-Prof. Here it's even bigger, and also here. So if your program has a lot of function calls, I need to do a lot of hooks on the function call and on the function return and a little bit of computation. So this can really get the overhead big over here. However, the other one that's pretty much getting the allocation functions do not impose too much overhead. Actually, it's very low overhead, except for the Placo one, which is still low but a little bit bigger, and which means that the Placo is pretty much like doing a lot of allocation calls, and that's why we have the overhead on time. I also measured the overtime regarding memory, and regarding LM-Prof, pretty much you will not see a lot of overhead. I'm pretty much getting pairs of callee functions and callers. So these pairs are not like many of them in one program. And however, if you take a look into the Lua memory profiler, you can see huge memory overheads in some cases. And first of all, the structure, it's a little bit bigger because I need to keep all the objects to draw them in the screen. So I need to have them in some structure. And the second thing is pretty much the size of the display itself. So if you take a look into very light ones, using not too much memory, you can see that you have a lot of overhead, but this is pretty much like the graphic memory, which is kind of a fixed size. If you take a look into higher loads of memory, higher uses of memory, you see that the display is not overhead itself. However, if you have a lot of objects, I need to keep that in memory. It's a little bit overhead. So some lessons learned. The first one is real time was useful to understand the location behavior. In some programs I could see what was going on and when, so if I should look into the beginning of the program or not, or at some specific part, so it can kind of give you insights. Of course my interface is not good, it should be much better, could be, but looking to real time, it's probably a good thing. The second thing is pretty much that ongoing interaction and data categorization was not very useful in our case. So first thing about data is that you cannot get a lot of information regarding different types in Lua. The second thing about ongoing interactions that the way I have implemented was not very flexible. So you could only do some small stuff. So going into that path could be good, but you need to really spend a lot of time in the interface so you can give a good interface to the user to play with the program. Fixed display was a bad choice, was really a bad decision. So if you have, for example, a program that uses a lot of memory, you need to kind of reduce the size of the object, and it's going to be very small and you cannot see anything. So, and you need to know before execution the size of the display, and figuring that out can be kind of tricky. So being able to redraw the display would be a good thing, and it's probably not very expensive. I thought it would be, but it was not. And finally, function profilers are very useful to new programs. So if you don't know the program, you have never read the code or anything like that, running a function profiler and get the information gives you an overview of the program. That's pretty much very useful to play around with that. The performance is okay for profilers. So when you're talking about profiler, so although you want to keep overhead to a minimum, it's kind of okay to have some overhead around, like 2 times, 3 times execution, depending on the use case. Finally, future work. So a wrapper to use the tools from command line. So now you need to manually open your program and put the first 2 lines and the last line. Just a wrapper, very simple, just to insert that for you and execute the program. This would be very helpful. Of course, a lot of interface improvements we need to do, many of them. So if you guys like it and want to play around, would be nice. Debugger interrogation. So one thing about ongoing interactions that pretty much like reprinting string is not very useful. It would be nice to kind of play around, print some variable, things like that. So kind of putting a debugger inside the profiler or making it available would be really nice. Add information of all function calls, so it's still open. At sometimes you are looking at the number of calls and you kind of get tricked if that's the total number of calls or the total number of calls that allocated memory. So maybe we could add this as a column. And play around with some kind of visual call graph. So instead of needing to be on your terminal and following the functions, just kind of print it in a nice way, nice view with some call graph. It would be really nice to have. So that's it. Thank you very much. And if you have questions. Oh,
no?
Yeah.
It's over there. Okay, we got one.
So you can also want to add like a tag to tables to be able to know, well, okay, this is my full tables, this is my, I don't know.
I'm sorry, I didn't get it.
To classify these are these kind of tables, these are the,
No.
these are,
And that's one of the issues about the typing.
So do you think it's a bad idea to avoid that, or it would be a nice addition?
No, I think it would be a nice addition. If you take a look into other projects, you probably get that. Like things that we kind of call kind of pretty printers, which is pretty much a function that you call passing an object and it kind of prints the object for you in a pretty way. You can use, for example, the graph vis1 and take a look into the graph and just for that table. So for one object, we already have things to do that. Even Lua Traverse, you can kind of use it to play around with one specific object.
Just not because I play with microscope and Lua Traverse, so to be able to add names to classes, so I could identify which where my memory was going to was all tables, but okay, which kind?
Yeah, I would need to find a way to kind of get this kind of information during the allocation, which I think it's not available at the time.
You can type,
So
you can type the stuff, right?
yes, you could do a lot of stuff regarding the object that you were kind of allocating and try to get some information and use it, but it would be like a completely, not completely, but a different implementation, and it would be very case specific.
So I was just thinking about adding a custom field underscore type and put a string there. And if, I don't know if in okay, the allocation function you have no way to access that. Answer myself. Okay.
Of the,
Just check, at least the prof is not available in Guarros. You consider?
yes, I consider the first one needs SDL, so not so sure how it would work. I don't remember if LuaRox installs this kind of dependency, but I think so. And but yes, it's just a matter of writing the rocks back and pretty much putting it, like the second library is pretty much doesn't depend on anything. So yeah, I'll try to. Thank you.